What if that soda can that you tossed into the recycling bin this morning could be back on the shelf in just 60 days, looking brand new and ready to go again? And that over 120,000 aluminum cans are recycled every minute around the world, fueling a billion-dollar industry that keeps the planet greener while saving massive amounts of energy. From collecting to melting, this is how 100,000 aluminum cans are recycled each minute in a factory. The journey of recycling aluminum starts the moment you drop an empty can into the recycling bin. From that small action, a massive process begins, spanning cities, industries, and even countries. The first step is collection, and it's a key part of this system. In the United States, consumers can take their used cans to redemption centers, earning small cash rewards while keeping millions of cans out of landfills. Europe runs on deposit refund programs and organized community collection drives. Brazil leads the world with an impressive 98% recycling rate, showing how national systems can make a huge impact. Once the cans are gathered, they're crushed and packed into giant bales. Each bale weighs up to 1,000 kilograms, about the size of a small car, and holds 65,000 flattened cans. Without this compression, loose cans would take up too much space, making transportation inefficient and expensive. But when packed tightly into these compact blocks, they're easy to handle and transport. These bales are shipped to major recycling centers like Novelis in the UK, or large plants in Japan, Germany, and the US. Upon arrival, they're stacked like giant building blocks, waiting to be broken down and recycled into something new. If you're enjoying this video so far, make sure to hit that like button and subscribe to the channel for more content like this. From here, the bales are placed on conveyor belts, heading straight for powerful industrial shredders. These shredders come with 340 horsepower and tear through the bales with ease. Inside, spinning blades rip the aluminum apart, shredding the cans into small, jagged pieces. The sound of metal grinding against metal fills the factory, creating an intense and chaotic atmosphere. But this isn't just about making noise. Shredding reduces the volume of the cans, making them easier to clean and quicker to melt down later. Before they can be melted though, the aluminum needs to be sorted. This step is crucial because aluminum, unlike steel, isn't magnetic, so it can't be separated using simple magnets. Instead, the shredded pieces move down conveyor belts at high speed and pass through an advanced optical sorting system. Infrared sensors scan the flow of metal, identifying and removing anything that isn't aluminum. Plastic, glass, or leftover labels. High-powered air jets kick these impurities off the line instantly, ensuring they don't contaminate the clean metal. Even with the optical system doing its job, some steel fragments might still be mixed in. To catch these, the conveyor passes under magnetic separators, which pull out any remaining steel. The process is incredibly fast, but the precision is impressive. What looks like a chaotic blur of flying metal is actually a carefully synchronized system, ensuring that only clean aluminum moves on to the next stage. Now that the aluminum is sorted, it still faces another challenge before it can be melted. The shredded pieces are often coated in materials like protective lacquers on the inside of the cans or colorful paint and labels on the outside. If these coatings are not removed, they can contaminate the melted aluminum and weaken the final product. To solve this, the shredded aluminum passes through high-temperature furnaces built specifically to burn off these residues. Inside the furnaces, the temperature soars past 700 degrees Celsius, hot enough to vaporize the coatings instantly. As the aluminum shreds pass through the fiery environment, you can almost imagine the heat radiating off the walls. The paint and lacquer are reduced to vapor within seconds, leaving clean, bare metal behind. Airflow within the furnace carries away the vapor to ensure it doesn't settle back on the aluminum. This step is critical because even a small amount of leftover residue could cause imperfections in the next stage, smelting. But molten aluminum doesn't cooperate easily. As it melts, it reacts with oxygen in the air, creating a layer of aluminum oxide called dross. This dross floats on the surface, similar to the foam that forms on a cup of hot coffee, but at extreme temperatures. If left unchecked, the dross could mix back into the liquid metal and lower its quality. Skilled operators step in here with long steel paddles, skimming the dross off the surface with precision and care. Skimming dross isn't just about scraping impurities off the surface. It's a combination of science and skilled technique. Modern recycling facilities often rely on flux agents, special chemicals added to the molten aluminum to help impurities stick together and separate more efficiently. Some plants even inject chlorine gas into the furnace. The chlorine reacts with unwanted particles, lifting them to the surface so that they can be easily skimmed away. This combination of manual skimming and chemical refining ensures that the molten aluminum is as pure as possible, ready for casting. Once purified, the glowing liquid metal is poured into molds to cool and harden. One widely used method is direct chill casting, where water sprays directly onto the metal as it leaves the mold, cooling it quickly and preventing cracks or defects from forming. The result? Massive ingots that can weigh up to 27 tons each and measure 10 meters long. It's astonishing to think that each of these giant blocks contains the recycled aluminum from roughly 1.5 million cans. These solidified slabs, or ingots, are the foundation for countless products. New cans, car parts, and even components for airplanes. As they cool, the metal inside becomes dense and strong, creating a perfect base for further refinement. Some facilities take a different approach, using twin roll strip casting to produce thin aluminum sheets directly from the molten metal. But for large-scale operations, casting large ingots remains the preferred method due to their versatility. Once the ingots are fully cooled and hardened, they're ready to be transported to rolling mills for the next stage of their journey. Here, they'll be reheated to around 525 degrees Celsius to relax the metal's internal structure and make it easier to work with. These massive slabs will then pass through powerful rollers that gradually flatten them into thin sheets. It's a bit like rolling out dough, only on an industrial scale. By the time they're done, the aluminum sheets are then as thin as 1/4 millimeter and ready to be shipped off to factories where they'll be transformed into new cans. To put it into perspective, these sheets are thinner than a grain of rice, but strong enough to be rolled into massive reels stretching thousands of meters long. Next, these large reels of aluminum sheets are then sent to can manufacturing plants, where high-speed machines get to work. Cupping presses punch out thousands of shallow cups every minute with remarkable speed and precision. But these cups are just the first step. They're then pushed through a series of forming rings, each one slightly smaller than the last. This gradual squeezing shapes them into the familiar aluminum can, with walls that are thin enough to be lightweight, yet strong enough to hold liquid without bending or breaking. Once the cans are formed, they go through a thorough cleaning and treatment process. Any grease, dust, or leftover particles from manufacturing are washed away, leaving them spotless. But it's not just about cleaning. Each can's interior is treated to prevent any reaction with the beverages it will contain later, ensuring the drink stays fresh and uncontaminated. Meanwhile, the can lids are made separately. Sheets of aluminum are cut into discs and pressed into perfectly formed lids. A rubber sealant is applied around the edges to create an airtight fit, guaranteeing that once the cans are filled and sealed, they stay that way. The pull tabs are molded and attached using precision machines, completing the lid's design. Interestingly, the technology behind this process is closely related to aerospace engineering. The aluminum alloys used to make beverage cans are very similar to those found in rockets, so the can holding your soda is more advanced than you might think. Economically, aluminum recycling is a giant. The industry creates over 100,000 jobs in the US and generates billions of dollars in revenue each year. By keeping materials in use and reducing the need for raw resource extraction, it plays a vital role in promoting a circular economy. This system ensures that products are continuously reused instead of being discarded, reducing waste and environmental harm while boosting long-term economic growth. Finally, after the cans are formed, cleaned, and sealed with their lids, they're ready for their final journey. They are then filled with soda, beer, or other beverages and shipped to stores around the world. The cycle doesn't stop there. In just 60 days, the can you're holding today could be collected, melted down, and reborn as a brand new can, clean, shiny, and ready to start its journey all over again. That's the beauty of aluminum. Endless recycling, endless possibilities. And that's how over 100,000 aluminum cans are recycled every minute, giving them endless new lives while saving energy and protecting the planet. Which part of the process surprised you the most? Let us know in the comments below. If you enjoyed this behind the scenes look, be sure to like, subscribe, and stay tuned for more fascinating factory processes. What happens to your old phone battery after it dies? Does it disappear, or does it have a secret second life? Every year, millions of discarded batteries are salvaged, stripped down, and reborn, extracting rare metals like lithium, cobalt, and nickel to build the technology of the future. Inside state-of-the-art recycling plants, a fascinating journey turns toxic waste into treasure. This is how 160 million batteries are recycled each year in a factory. Before a battery can be replaced, it has to be collected, and that's more important than it sounds. Left in landfills, batteries can leak harmful chemicals like lead and lithium, polluting the environment. In Germany and Sweden, strict laws require people to drop off used batteries at supermarkets, electronics stores, and recycling centers. In North America, collection is most voluntary, with programs like Call to Recycle setting up drop-off locations, while companies like Tesla and Apple recycle old batteries directly. Once collected, the batteries are transported in specialized trucks to prevent leaks or overheating, ensuring they reach recycling facilities safely, where the real transformation begins. Not all batteries are the same, and that's why sorting is such a critical step. Each type, lithium-ion, nickel metal hydride, lead acid, and alkaline, needs a different recycling process. Mixing them up could cause serious problems, so accuracy is key. In smaller facilities, workers manually inspect batteries, checking labels, size, and shape to determine their composition. But in high-tech recycling plants, machines do the heavy lifting. Spectroscopy and X-ray scanners analyze each battery in seconds, identifying its metal content with pinpoint accuracy. Batteries travel down high-speed conveyor belts, where AI-powered cameras and sensors detect anything out of place. If a battery doesn't match the right category, it's instantly removed. This automation speeds up the process while ensuring precision. Electric vehicle batteries, which are much larger, require special handling. Robotic arms carefully dismantle them, breaking them down into smaller modules before recycling. This is where things get intense. Batteries aren't just metal and plastic, they're packed with stored energy, which makes breaking them down a tricky process. If a charged battery is shredded without the right precautions, it could catch fire, explode, or release toxic fumes. That's why safety comes first. To prevent accidents, high-risk batteries, especially lithium-ion ones, need pre-treatment before shredding. Some are frozen in liquid nitrogen to neutralize any remaining charge. Others are placed in sealed chambers filled with inert gases to eliminate any risk of combustion. Another method involves controlled electrical discharges, where small, precise currents drain out any leftover energy. Once these safety measures are complete, the real breakdown begins. Batteries are fed into massive industrial shredders equipped with razor-sharp steel blades. These machines tear through casings, grinding batteries into tiny pieces. Some shredders spin at over 2,000 revolutions per minute, creating an ear-splitting mix of clanging metal and snapping plastic. In just seconds, a solid battery is reduced to a chaotic mix of metal shavings, plastic bits, and a fine dark powder known as black mass, the most valuable part of the recycling process. At this point, the shredded material is a mess of different components: aluminum, steel, copper, plastic, and black mass, all mixed together. Separating these materials is the next big challenge, because improperly sorted elements can contaminate the final product, making it harder to reuse. The process starts with powerful magnets positioned along conveyor belts. These pull out ferromagnetic metals like nickel, iron, and cobalt, which are key ingredients in new battery production. Nickel and cobalt are especially valuable, but leftover steel from battery casings can interfere with the purity of the recovered metals. To fix this, some recycling plants use variable strength magnetic separators, which fine-tune their pole to extract only the desired metals while letting the others pass through. While magnets work well for iron-based metals, non-magnetic materials like aluminum and copper need a different approach. That's where eddy current separators come in. These machines generate electromagnetic fields that repel non-ferrous metals, pushing aluminum and copper into separate collection areas. This ensures that high-purity aluminum can be used in new battery casings, while copper, commonly found in battery wiring, can be repurposed for electrical applications. With the metals removed, what's left are the lighter materials, plastic casings, and paper residues. These are separated using high-speed air jets, which blow away lightweight debris. Some recycling facilities go even further, using fluidized bed separators that combine air and vibration to lift and separate materials with extreme precision. This level of detail ensures that only the purest, most valuable elements move forward. But the real prize in battery recycling is the black mass. This fine powdery substance is packed with lithium, cobalt, manganese, and nickel, the most sought-after metals in battery production. Extracting these materials requires specialized chemical processing, where advanced techniques break down black mass into reusable raw elements. Once collected, it's sent off to chemical processing facilities where the final transformation begins. Now comes the real science: the stage where valuable metals are extracted from the black mass and turned into reusable materials. The process needs to be precise, efficient, and environmentally responsible. Recycling plants use two main methods: hydrometallurgy and pyrometallurgy. Many facilities combine both to get the best results. Hydrometallurgy is the more common method because it allows for highly selective metal recovery. This process works by soaking the black mass in giant vats filled with acidic solutions like sulfuric or hydrochloric acid. These bubbling chemical baths dissolve the battery materials, breaking them down into their base elements. To separate them, special chemical reagents are added, binding to specific materials and isolating them one by one. Lithium is the first to be extracted, appearing as lithium carbonate, a fine white powder similar to sugar. It's then purified and sent off to be used in new battery production. Next is cobalt, one of the most valuable metals in the process. It crystallizes into a striking blue material, which can be refined further for use in battery cathodes, aerospace technology, or even medical devices. Nickel comes last, forming a pale green compound known as nickel sulfate, a key ingredient in batteries and stainless steel manufacturing. One of the biggest advantages of hydrometallurgy is its energy efficiency. Compared to high-temperature methods, it uses less power, produces fewer carbon emissions, and allows for the recovery of multiple metals at high purity levels. But some materials are too stubborn for acid baths and need a more intense approach. This is where pyrometallurgy comes in. Unlike hydrometallurgy, which dissolves metals in liquid, pyrometallurgy relies on extreme heat to melt and separate battery acids. The shredded black mass is fed into massive electric arc furnaces, where temperatures reach nearly 3,000 degrees Fahrenheit. As the materials melt, they naturally separate based on their density. Heavy metals like cobalt and nickel sink to the bottom and are collected in liquid form before being cast into solid ingots. Lighter elements, such as lithium and aluminum, rise to the surface, forming a layer called slag. This slag is then processed separately to extract lithium. To further refine the molten metal, flux agents, chemical compounds that attract impurities, are added. These impurities float to the top and are skimmed off before the metals cool. Once the metals are fully extracted, they move on to the final stage, cooling and solidification, where they take shape before being sent back into manufacturing. Once purified, the molten metals must be carefully cooled and cast into solid ingots. Large rectangular blocks of raw material can be easily transported and processed. The cooling process is crucial because if the metal solidifies too quickly, it can develop structural cracks, making it unusable for high-performance applications. To avoid this, recycling plants use specialized cooling chambers that regulate temperature changes in a controlled manner. There are multiple cooling methods, each designed to produce high-quality metal ingots. Air cooling is one of the more common methods. Large industrial fans blow cool air over the molten metal, gradually lowering the temperature until it solidifies. This method prevents thermal shock, ensuring that the final product remains its strength and integrity. Water cooling is another widely used technique. Red-hot ingots are carefully submerged in water tanks, creating dramatic bursts of steam as the metal rapidly cools. This process speeds up solidification, but must be carefully managed to prevent internal defects. Some facilities use a combination of both, starting with air cooling before transitioning to a water bath. This hybrid method ensures a uniform cooling process, producing high-strength ingots that can be reintroduced into the supply chain. Once cooled, these shiny ingots, containing purified lithium, cobalt, nickel, and aluminum, are inspected for quality. Any imperfections are identified and corrected before the materials are shipped out for reuse. The recovered metals have countless applications. Lithium extracted from old batteries is used to manufacture new lithium-ion cells, powering everything from smartphones and laptops to electric vehicles and solar storage systems. Nickel is an essential component in wind turbines and stainless steel, while cobalt plays a crucial role in medical devices such as pacemakers. Beyond just resource recovery, battery recycling is helping to reduce dependence on environmentally destructive mining operations. Extracting 1 ton of lithium through traditional mining methods consumes nearly 500,000 gallons of water, a staggering amount that can be avoided through efficient recycling. As demand for batteries continues to grow, recycling technology is evolving at a rapid pace. With breakthroughs in direct recycling, more efficient chemical extraction methods, and increased government support, we are moving toward a world where nothing goes to waste, a future powered by sustainable energy and smarter resource management. And that's how 160 million batteries are recycled each year, turning old, worn-out power sources into brand new materials that drive the future of technology. Which part of this process surprised you the most? Let us know in the comments below. And if you enjoyed this behind the scenes look, make sure to like, subscribe, and stay tuned for more fascinating factory processes.
What if we told you that every glass bottle you toss in the recycling bin can come back as a new bottle in as little as 30 days? Or that recycling glass saves enough energy each year to power entire cities? From the shattered remains of bottles to the glowing furnaces that melt them into a brand new future, this is how 100 million tons of glass are recycled every year in factories across the world.
Glass is an incredible material. It's durable, versatile, and endlessly recyclable. But here's the thing, it doesn't decompose. A single glass bottle can sit in a landfill for up to 1 million years. That's right, 1 million years. Thankfully, we found a way to turn this environmental challenge into an opportunity through the marvels of glass recycling. The journey begins with collection. Around the world, glass is gathered through a variety of systems tailored to local infrastructure and habits. Many cities rely on curbside collection programs where residents separate their glass waste into specialized bins for easy pickup by waste management trucks. In other areas, centralized drop-off points allow people to bring their glass items to dedicated containers, often sorted by color. Some regions incentivize recycling through deposit refund systems, where returning bottles can earn small cash rewards or grocery discounts. In European countries, this is a routine practice, fostering widespread participation and higher recycling rates. Conversely, in some parts of the world, glass collection is carried out informally, often by marginalized groups who sell the gathered glass to recycling facilities. Once collected, the glass is transported to sorting centers or recycling plants. Trucks filled with glass bottles, jars, and other items deliver their cargo to facilities designed to handle large volumes of material. At the plant, the first step involves unloading the glass into holding containers, where it's prepared for the next stages. The process may seem straightforward, but it's far from simple. Sorting is a crucial step in glass recycling. Glass comes in 3 primary colors: clear, green, and amber, and each has specific uses in manufacturing. Mixing colors can compromise the quality of the final product, so sorting by color is essential. This task is handled by advanced optical sorting machines equipped with lasers and sensors. These machines analyze each piece of glass as it moves along a conveyor belt, identifying its color based on the light it reflects. Once identified, the machine uses air jets or mechanical systems to direct the glass into the appropriate category. These machines operate at remarkable speeds, sorting tens of thousands of glass fragments every minute with incredible accuracy. But sorting by color is only part of the equation. Contaminants like labels, caps, adhesives, and food residues are some of the biggest challenges in glass recycling. Removing them require multiple stages of cleaning. First, magnets extract ferrous metals, such as steel caps, while electromagnetic separators tackle non-ferrous metals, like aluminum. These systems are powerful enough to remove even tiny fragments that might otherwise go unnoticed. Next, pneumatic systems blow away lightweight contaminants, including plastic and paper, using controlled air currents. For glass intended for food or beverage containers, wet cleaning processes ensure thorough removal of stubborn residues. These washing systems use water jets and mechanical scrubbers to eliminate adhesives, dirt, and organic matter, leaving the glass spotless. This meticulous process is essential for maintaining the quality and safety of recycled glass products. Once the glass is clean and sorted, the next step is crushing. The glass is fed into powerful crushing machines, which break it down into small, uniform pieces known as cullet. These machines come in various types: hammer mills, jaw crushers, and gyratory crushers, all designed to reduce the glass to a specific size. For instance, hammer mills pulverize the glass with rotating hammers, while jaw crushers use a stationary plate and a moving one to crush the material. After the initial crushing, the cullet is sifted using vibrating sieves. These machines separate the glass by size, ensuring a consistent particle size for the next stage. Oversized pieces are sent back through the crusher to minimize waste. Uniform cullet is easier to handle and melts at low temperatures, making it an essential part of the recycling process. Also, cullet melts at a lower temperature than raw materials, saving significant energy during the production process. Crushing is not just about reducing the size of the glass, it also makes the material easier to handle and prepares it for melting. Now comes to the melting stage, where the real transformation begins. The cullet is transported to industrial furnaces that operate at temperatures as high as 3,000 degrees Fahrenheit. Inside these furnaces, the cullet liquefies into molten glass, ready to be shaped into new products. One of the most significant benefits of recycling glass is its energy efficiency. Because cullet melts at a lower temperature than raw materials, it reduces energy consumption by up to 30%. Every ton of recycled glass saves more than a ton of natural resources, including sand, soda ash, and limestone. Many modern furnaces are powered by renewable energy sources like wind or solar, further minimizing the environmental impact. Massive electrodes inside the furnaces sustain the intense heat, while sophisticated systems regulate the temperature and prevent energy loss. Once liquefied, the molten glass is shaped into new products. The liquid is poured into molds to create items such as bottles, jars, and decorative objects. Factories rely on automated systems to ensure precision in shaping, with molds designed to meet exact specifications. But recycled glass isn't limited to traditional uses. In the construction industry, for example, it's used as an aggregate in concrete and asphalt, adding durability and aesthetic appeal. It's also transformed into fiberglass insulation, which helps improve energy efficiency in homes and buildings. Beyond that, recycled glass finds its way into art and design projects, becoming countertops, tiles, and decorative elements. After shaping, the glass is slowly cooled in a process called annealing. This step is very important because it prevents cracks and makes the glass strong and durable. Once the glass is cooled, it goes through quality checks. Machines with cameras and sensors inspect each piece for problems like cracks, bubbles, or uneven shapes. Any item that doesn't meet the standards is sent back to the start of the recycling process, making sure nothing is wasted. But the process does face some challenges. Contamination is a big problem, especially when materials like Pyrex, ceramics, or heat-resistant glass mix in. These materials melt differently and can disrupt the recycling process. To solve this, advanced sorting machines, including AI-powered technology, are being used to detect and remove these items more effectively. Transportation is another issue since glass is heavy and costly to move over long distances. Many recycling plants are now focusing on local operations to cut down on these costs and reduce emissions. New technology has been essential in solving challenges in glass recycling. AI and automation have made sorting and processing much more accurate. Some factories now use closed-loop systems, where recycled glass stays on site and is reused without leaving the facility. Lightweight glass designs are also becoming popular because they use less material and are easier to recycle. These innovations are making glass recycling more sustainable and cost-effective. The environmental benefits of recycling glass are huge. Every bottle recycled means less waste in landfills and fewer greenhouse gases released into the air. Unlike many other materials, glass can be recycled endlessly without losing its quality. This makes it one of the most sustainable materials that we have. Recycling also saves natural resources, like sand and limestone, and uses much less energy than making new glass from scratch. Together, these benefits show how important glass recycling is for protecting the planet and fighting environmental problems. The uses for recycled glass go way beyond making new bottles and jars. In construction, crushed glass is used in roads and building foundations because it's strong and eco-friendly. In farming, tiny glass particles are used to improve soil by helping it hold water and stay healthy. Artists and designers also love recycled glass for making countertops, tiles, and other creative pieces. It's a great example of how recycling can lead to innovative and useful ideas. Looking ahead, the future of glass recycling is exciting. Governments and organizations are working on better ways to collect and recycle glass while encouraging more people to participate. Scientists are developing systems where glass can be recycled endlessly without any waste. New technologies, like AI sorting machines and furnaces powered by renewable energy, are making recycling faster and better for the environment. With these improvements, glass recycling is set to become a big part of creating a greener and more sustainable world. And that's how over 100 million tons of glass are recycled every year, from the initial collection to the advanced sorting and melting that turns waste into valuable new products. But before we go, we want to know, what's your favorite recycled glass product? Let us know in the comments below. If you enjoyed this video, don't forget to hit subscribe so you won't miss out on more behind the scenes looks at fascinating factory processes.